Okay, welcome back everybody. This is not the first day of class, although I don't have a video record of the last class, even though I tried to record it. This happens about once a semester, so we've already got it out of the way. So usually the technical issue is me, so messing something up. I'd have the camera in slow motion, so I've got like 50 minutes of me moving, no volume. I was going to post it. I was looking at it last night. It's really unflattering watching yourself and your face move, slow motion. So I'm not even going to show it to my wife. You guys don't get to see it. I apologize. So I'll just recap real quickly what we went through. So we went through class structure. We just had a conversation briefly about maybe a little bit about Bayes, but not too much so far. It was mostly class structure stuff. So I'm just going to race us through that real quick, what we covered. The web page is www.apps.stat.et.edu, and then you have to append my last name, Lehman, to this, just like that. So that's the special part right there. Slack, I'll have a Slack page soon. The reason I'm waiting on that is when I make it at the very beginning of classes and people are still in their shopping mode for classes, I'll forget to email it to somebody, the invite link. So I want the class to settle into place a little bit, so I'll probably build that on Friday and send it out to everybody so I have a correct roster that I pull down off of Canvas. I don't use Canvas for anything. All the materials are on my webpage. I'll show you that later in just a moment. I also use a YouTube page to carry persistent videos in the events that my videos actually record correctly. So if you're ever missing a video or you want to get ahead, I have videos from previous classes as well. I'll walk you through that in a second. Just a couple announcements that we went through. Midterm 1 is October 30th. It's in class, so we're going to do it the old-fashioned way. You sit here, and you're going to get a pen and a piece of paper. So you'll get that. You won't get a calculator. I won't be asking you to do any calculations where a calculator is actually required. If you're supposed to multiply a bunch of numbers together and sum them together or something like that, just write down the equation. So I don't need what it's equal to at the end of the day. So I don't need to know that the number is 5.26. I know that a lot of instructors will do that, and they'll grade you on your long division and things like that. I'm uninterested. So I'm going to be looking for process, whether or not you know the concepts and things like that. So if the process is correct, then I will consider your answers correct. Okay. That will be on October 30th. The first homework is out, homework 0. I call it homework 0 because it's not very technical. It just asks you to walk through and compute a posterior expectation. I can even tell you how to do that in the future. If you're concerned how to do it, I kind of walked you through real quickly on homework 0 how you would solve that problem. There's also a paper I want you to read. It's called When Did Bayesian Statistics Become Bayesian? We'll look at that paper in a moment. The question is when did we formulate the moniker Bayesian Statistics? And there's a long paper written about that, and I think there's a couple good answers in there. So I'd like you to read that just to understand that this stuff is a blossoming field, what people have done, their contributions to the field, and sometimes you learn why people did things through history. Why did they make the choices that they make? And are those choices still the choices we would make today? So a lot of times we make choices because that's what's in the textbook. Why did we make that choice on the textbook? Because that's what they made last year. They did that the year before, and they did that all the way back to the 1920s. We're still using the same text. And the question is should we be using the same techniques? And I think the answer is techniques evolve with computation. And so we'll be studying that as well. Kind of the fundamentals of Bayesian statistics, but also the computational side of Bayesian statistics. If you go to this web page, it will bring you here. So this is the cover. A little bit about me. Some stuff. This is the link you'll click on. Course is taught. Your course is this one, Bayesian Statistics. If you like to see some other courses and homework assignments and things like that, those are all in place for this homework, for those classes. For the Bayesian Statistics class, I've updated the entire schedule for the class. So I consider this a tentative schedule. I might adapt the dates on the schedule. I might adapt the assignments, and I'll let you know through Slack when we post Slack. So I'll be updating you and messaging you through that. But a lot of the stuff that you're going to be going through in the class is going to be on this page. So if you click on the Bayesian Statistics link, you'll come here, and this is the most important part that you'll be going to regularly. So there's already live links with homeworks on here, with papers that you can download, with due dates that match 2023. So those are tentative due dates. The only one that I want to lock in place is this one right here. So Introduction to Bayesian Statistics, when did Bayesian inference become Bayesian? You're going to read that, and there is a homework 0 out. It's right here. You'll click on that, and it'll bring you here. So to this PDF. So read the article, when did Bayesian statistics, Bayesian inference become Bayesian? So italicize Bayesian, it's the word we're looking for. So when did we start calling it Bayesian statistics and attributing it to Bayes? And then there's some questions in here. Who's the founder of Bayesian statistics? I guarantee if you punch that into Google, it will not give you a concise answer. ChatGPT will not give you a sensible answer. It'll write an article for you. So, but it won't tell you anything sensible. But Steve Feinberg did an exemplary job of outlining all of this. So I'm not suggesting that you read every word in that paper. I'm suggesting you learn how to skim fast. Pick up on names, back up, learn how to read around the names that you see. If there's things that are interesting, you go and you read that. I almost never linearly read something. So I usually open up the paper, I start looking at what the sections are, I read the introduction, I read the conclusion, and then I start filling in the middle. And I'd suggest you do something like that as well. So if you ever try to read a textbook linearly or a paper linearly, you're going to get lost real quickly. So you want to have some idea of what you're navigating in advance. So nice thing is there's no technicalities in the paper. So it's all just a historical record of who did what and when. And they answer all these questions in some form. So who originally coined the term Bayesian? Who came up with the term first? This could mean one of two things: who used the term first, or it could mean who popularized the term. And I'm not going to distinguish those two things. What I'd like you to do is just write a couple sentences. So, and if you'd like to equivocate that I think this person deserves credit, but I also think this person deserves credit, and this is why, that's usually a good answer. So, usually answers aren't just absolute. There's some variation to those answers. That's what we'd be studying in Bayesian statistics as well. So give me the posterior distribution of these answers. If you understand, there's a joke buried in there. Okay, and then compute the expectation of theta given x based off of these two things, the prior distribution and the likelihood function. The likelihood function is a function of theta, and that's the reason I put theta on the left of the bar. I'll be going through this notation. It's not consistent in the statistical universe. Different people use different notations for likelihood functions, and I'd like to start off talking about that when we delve into what did Bayes do and what did people do following that. So I'll give you a brief explanation of all of that in just a minute. So one pager on the homework. So that's due on September 1st. So start reading soon. I also typically will give you the LaTeX file that I use to compile everything. This is just so if you're learning LaTeX, you have a template that you can start with, kind of see how things work. But the way people learn LaTeX is they go to Stack Exchange usually. You type in LaTeX, and you usually have to append something mathematical, otherwise it's going to take you to another variant of sites that are non-mathematical. And they won't pronounce the term LaTeX, it's LaTeX. They'll say LaTeX. So, and this isn't latex, it's not a fabric. So, it is LaTeX. So, TeX is a technical formatting language that was created a long time ago, and Leslie Lamport adapted that language so that it's a little bit easier to use. So there's more macros in LaTeX. So most people will say LaTeX. If you don't want to use LaTeX, that's fine, but you probably should be exposed to it if you're formatting mathematical things. So Word is probably not your best facility for that. So once you learn the commands, you're much faster than going to a palette and clicking on things. So LaTeX files will be included on several of the homework sets. So there it is, there it is, there it is. So the first several will come with the LaTeX file. They might all have the text file. Looks like they all have the text file. We'll be also reading papers throughout, and those are kind of listed on the left-hand side here. So you can navigate that and kind of look at everything. Again, this is the schedule. I'll try not to modify this here, but instead make memos on Slack if I adjust any of this. So what do I mean by adjusting? I usually mean that I might delay a due date. So I don't think there's a case in here where I'll need to accelerate one. Okay, so everything will be in your favor. Any questions about all that? Cool. So we went through most of this last time. You can also go to the syllabus. That's here. So these are the logistics of the class. The important parts that you'll want to remember is the final exam date is December 13th, Wednesday at 10:05 a.m. So ends at approximately noon. So that's the morning. So lucky for us, it's not the 7:45 slot. So I've had to do that several times, and you almost have to prepare for 2 weeks just to get yourself in that rhythm. So it's pretty close to the time we'll be thinking about Bayesian statistics. So we'll train ourselves to wake up 2 hours early for the final. TA office hours, they'll be Zoom-based. UEE will come in on Friday at the beginning of class, and I'll give you an introduction to him. So he'll be there to help you on Zoom, possibly to run some of the review sessions. The review sessions are scheduled for, they're right here, Thursday, 6 p.m., about bi-weekly. It's probably really small. So about bi-weekly. We will not do a review session tomorrow. I will try to reserve this room at 6 p.m., but if one of the clubs beats me to it, I'll try to get something close. So I'll be messaging everybody with the location of the review sessions. Right now, we don't have one scheduled. We probably don't need one for next week as well. So I'm probably be in the third week is what I'm anticipating. Okay. Midterm, October 30th, one midterm. Information about the book, which I think is a very good reference. You'll be wanting to read about things outside of the class. I'll try to be as thorough as possible, but different people think about Bayes a little bit differently. And I would encourage you to read as much about it as you can. And so sit back and think about these things. Probably most of you know there's a lot of philosophical debates out there, and what are people debating about? It's not things that they totally agree on. And so sometimes they're both everybody's debating about things where everybody's wrong. Sometimes there's debates where one person is more right than others. And sometimes you'll get debates on interpretations, but they have the same answers. I like that last debate. I usually go, there's no debate. This is great. We can all have everything. So, and in some cases, that will happen in our analyses, and we'll see some of those soon. The breakdown of the course is 40% on the final exam, midterm 30%, homework problems, 30%, pop quizzes, may be sprinkled in throughout the semester. I'm still deciding on that. So you can look at the breakdown of grades, but probably what I need to show you is what the distribution of grades actually looks like this semester. And my assumption is it's not always the same. I've noticed some patterns in the grade distributions. I've noticed them change over the years, and I'm curious to see what we get this year. So when we get a distribution that's kind of filling out, we have enough data that we can actually look at a histogram, I'll walk you through where you're at in the class. My hope is that everybody can get an A in the class. So I have no problem giving an A to everybody. These are minimal. These are, I would say, your least upper bounds. If you know what that means, on the grades. So they might come down a little bit. Academic honesty, do your own work. You're allowed to collaborate, but you are not allowed to plagiarize off of each other. So if I catch it, I'll give you guys a warning. If I have to have a conversation with you twice, probably the graduate honor system will be invoked. So I don't think that it's too much to ask that we all try to do our own thinking, but if we get stuck on something, definitely go to your friends, people in the class that can help you. This is a learning environment. So at the end of the day, I just want to make sure that what we're grading and looking at is a representation of what you believe you know. So if you don't know something, we can try to help you with that. So outside of office hours, I'm always available for about a half hour after class. That's not true today because I booked a meeting. So, but if you ever need a meeting or something like that, send me an email. We'll slot it in. I'll try to make myself available after classes, especially around test taking time, and we'll do a few more review sessions around test taking time as well. And if you ever want to request a review session, you can do that as well. If I don't intend to give one, but you really want to talk about something, I can come in and talk about that. Okay, so that's the syllabus. That's posted. You've got the schedule. Boom, there it is. I think that's most of the logistics. We also have the course lectures that are videotaped. So this is the name of my YouTube page, Lehman Lectures. So pretty straightforward. Lehman is my last name. And you can scroll through this. Once I put up a video, you'll see it first in line right here. So I haven't put up a video since May of 2023. So the last day of classes. If you want to go back all the way to the Bayesian Statistics course from last year, those videos are still active online. So you can just scroll back, and I think this is the first one right here, 8/22/2022. So if you're ever looking to get ahead or something like that, or you need some review, and you're wanting to get ahead and not look backwards by looking at the video that I post most recently, there's opportunity to do both things. Click on those. Oh boy. Hello. Grammar. Do you guys use Grammar? So here it is. And I think I would need to activate the volume. These do have volume. I checked last night. So we probably have to turn on the speakers here. We won't do that this time. But you can look through this. And this is about what your lecture is going to look like today. So approximately. So the Lehman Lectures, persistent videos, I'll post them about every other class. So I don't want to get too bogged down. It takes a long time to post 3 hours of high resolution to YouTube, but posting 2 hours, I can deal with that. Usually it takes about an evening to upload everything. So be patient with those, but I'll try to get them out to you. I tried to get that video out to you so that we could look at it today. Unfortunately, I made a mistake. Any questions about the class structure, please?
Can you go to the class structure page? Because when I was looking at it, it kind of looked like it cut off after September 27th, because then it jumps to like extra credit there. But
oh, I stopped filling in the dates.
Oh, okay.
So there's due dates that are posted here.
Okay.
So in the middle, yeah, I kind of stopped doing that because I'm like, I don't know exactly what date we're going to talk about this, but I kind of know when things are due. So if you look over here, those are valid. These are approximate, and I did fill in a couple of those just to give us some structure. I need to know where to start. I need to know where to finish, and then I kind of, maneuver the rest. Yeah, good eye. Anything else? I was thinking we'd just go until September 27th, and then I would see you again. No, I'll be here every day. Okay. That's that. Slack page will be coming soon. Let's do an intro to Bayesian statistics. Just kind of learn what is this stuff that we're even talking about. I'll present you with an example problem as well. How's that? Okay. Not the correct date. That was 2 days ago. So we're already a little bit behind, but I was being ambitious and trying to accelerate everything. So we're right on time. Let's see. View full screen. Great. Good enough. Okay. We're going to discuss this part of everything. I'm going to get into Monte Carlo a little bit later in this class. So I'm going to give you the first part of this presentation on Bayes' theorem. Where does it come from? How do Bayesians use Bayes' theorem? So I will point out, everybody acknowledges Bayes' theorem. What Bayesians do with Bayes' theorem is a little bit different than what you might have learned in your Stat 101 class. So very often people would give you a conditional distribution and tell you a probability in your Stat 101 class. I'm using that term metaphorically. So give you some prior distribution and ask you to work out the posterior distribution from everything and invert everything. So you don't have to be a Bayesian to do that. If you knew those probabilities and you've established those probabilities, maybe off a frequency or something like that, you could invoke Bayes' theorem and still be a frequentist, and everybody agrees. So the problem I have with the Stat 101 variants of Bayes' theorem is that because you use Bayes' theorem doesn't make you a Bayesian. It's the way you use Bayes' theorem that makes you a Bayesian. So we'll try to distinguish that a little bit today. As I pointed out last time, back in 2007, I did a Google trend search on the term Bayesian and other root versions of it, Bayes' theorem. You might be asking, how do you even pronounce the word Bayesian? There's 3 typical pronunciations. I say Bayesian. So there's also Bayesian. You'll hear people say that. You'll hear people say the hybrid, Bayesian. So the only reason I say Bayesian is because his name is Bayes and not beige. So, but I've heard it that way. And so you don't need to stop and correct anybody or ask them about it. Different people say the word differently. So if you're ever singing the term, singing Bayesian is a little bit difficult to say, so then you might say Bayesian. So I've used that once in my life. I made a song about Bayes' theorem. I don't remember it. Anyway, what we notice is that the term Bayes is being used more and more through the literature. So what Google does is it looks for dates of articles, not when they've submitted the article, because Google wasn't around back in 1760, but it looks for occurrences, co-occurrences of the word Bayes, and certain dates. And this is what it finds, that the term has been increasingly more used. And that's why you guys are here, and it's probably a big explosion right out here. I think that the falling off pattern is not because the term is being used less and less as we approach the date in which I did the query, but rather Google has a problem with documenting history. New stuff it's unaware of, and old stuff it's aware of. So stuff that was published on Google 10 years ago, it's very aware of it. And stuff that was published yesteryear, search engines might not have found all of that. And so they have crawlers, and they're coming up with a persistent view of the internet, but it does take time. So we notice that the term appears frequently way back in the 1760s. We'll study that date, 1763, in just a moment. That's actually Bayes, and Bayes writing his initial paper, which coincides with Bayes' death. So I'll also point out Laplace was hanging out around this period, and he took note of everything. So 1920s, there's an occurrence of the word Bayes. There's actually a lot of occurrences, and I'll point out that these are some statisticians you might have thought are classical statisticians who might actually be Bayesians. So again, what we write in textbooks is sometimes half a story. Then we start to see that Bayesian statistics get some popularity. And it's kind of, people are playing around with it and they're formulating the field. I would say this is the time period where Bayes became Bayesian. So people weren't using that term here, and they certainly weren't using it back here. So people start adopting the term Bayesian and it starts getting popularized around this period. And then there's a launch. And I would argue that this launch is probably because of Monte Carlo. And so computational facilities, that we can start carrying out Bayesian procedures and not just arguing about if we could carry out Bayesian procedures, our answers would be better than yours. So they're not arguing on philosophical terms, but they're arguing through applications. And that seems to be a little bit more compelling in some cases. So Bayes is becoming more and more popular all the time. There's two things that Bayes does, and I would argue that those are the reasons why it's popular, and we'll have to get around to those reasons later. Please.
I was just wondering, because there's a tail off at the end towards 2007 whenever you did this, right? So why do you think that is?
I think it's because of the way a web crawler works.
Okay.
So that if I just publish something, so all of my articles that I publish this year, Google might become aware of them next year.
Okay.
So I think it's just that it has a harder time with your most recent stuff.
Okay.
So a lot of times when I go to Google Scholar, I know the administrators look at it, that I have to go and tell it on my Scholar page, I've written this paper or I'm a co-author of this paper. Sometimes they'll miss that I'm a co-author. And unfortunately with my name being Scotland and several variations running around out there, it sometimes doesn't know who I am. So it could be worse. I could be like John Doe or something like that. So I know that's not a real name. I don't know, I've never met that guy. But I don't want to use somebody's name that might be in the department. So we do have those with very common names sometimes. And it confuses those as well. So I think it's just, it's easier to search for things that are well known. Here's my evolutionary tree of Bayesian statistics. I can never talk about Bayes without talking about non-Bayesian ideas. So I always have to deal with compared to what? What are other people doing? Why is this different? So to understand what something is, I need to understand what it's not. So, and that's really difficult sometimes. We've all done this when we go Amazon shopping or something like that. We see a product, it tells us all these glowing reviews. We go to another product, and it tells us some glowing reviews. And what we really need is the diff between those two things. How are they different? So they're usually not forthcoming about those. This is my tree right here. I'll just kind of zoom in. Does anybody notice anything interesting about the tree? I'm sure some of you do immediately. So top of the tree is maybe our most recent common ancestor in genealogical terms. So where everybody combines, and then it leaves of the tree, the nodes, that's more modern day statisticians. Again, I made this a long time ago. So there's even more modern statisticians. This is the problem with trying to be modern, is it wears off. Anybody notice anything interesting about my tree?
You've got split up into sections.
I do.
There's a left box with.
Yeah, so I kind of gave you some boxes here. So these are who I typically think are non-Bayesians. And these are Bayesians. So yeah, there's kind of a left and a right-hand side of the tree.
How come on the Bayesian side it splits up even more? It's got two other branches.
Because this is Bayes. This is Bayesian statistics. I happen to be a Bayesian for the most part. So because this is Stat 544, I've oversampled the Bayesians. So this happens in statistics as well. Sometimes we oversample our interest group. And so we're not good at comparing our interest group to other groups. So sometimes we have to stratify and adjust everything. So this was just sampling bias. So I wanted to tell more of a story here. I would say that a lot of the classical ideas out there are classical for a reason. Classical means it's old in some sense. So if you think about the term classical literature or classical music, we're usually thinking of something that is dated. So anything else you notice about my tree? Please.
I don't see Bayes.
Where's Bayes? So where the heck is Bayes in the tree? I rooted the tree at Laplace. And no disrespect intended to Bayes. I think he was really onto something It's unclear to me if he carried out Bayesian analyses the way that we think about Bayesian analyses these days. He certainly came up, or was the first one to write down Bayes' theorem that we know of. But I don't know if he knew how to extend that to what I would call real parametric Bayesian analyses. There's also non-parametric variants of Bayesian analyses. We can talk about those later in class. But for the most part, this class is a parametric approach to doing Bayes. Laplace was doing that a couple years later. So I think Laplace understood the extension to what Bayes said. So I usually argue ISBA, the International Society for Bayesian Analysis, instead of spending $1,000 every year to go polish Bayes' grave, they should go take some of that money and go polish Laplace's grave. So they actually spend about $1,000 a year on this, and somebody goes over there and does this thing. It's kind of cute. So, but Laplace, I think, may have understood a little bit more. Now, of course, we can't go back and ask these people, so that's my opinion. So I'm certainly not saying that Bayes doesn't deserve some credit here. He obviously gets enough already. This kind of branches off into Carl Pearson and Fisher. There probably should be a big fork between these two fellows because they had a lot of tiffs with each other and disagreed on quite a lot of things. Some of the stuff that they disagreed on, from my practical understanding, it's like we would never know the truth and it doesn't matter because we're going to carry things out exactly the same. So Pearson thought that a sampling distribution, what we were measuring is our measurement imperfections out there. And everything had a common value and the states of that common value could change. And that's what gave variation to a histogram. Where Fisher thought that it was strictly measurement error that we were making. And it could be both. You know, that's the data we got. You know, we tried to control the variation on it. And it doesn't really matter how that variation in the data really arose. So there's a lot of arguments out there about determinism and stochasticity. And I've heard that argument for a lot of time, and I usually think it doesn't matter. So, you know, it's almost like if a tree falls in a forest. I know the answer to that question, but the real answer is it does not matter. So anyway, there were some extensions to these, Neyman and Egon Pearson, which was the son of Carl Pearson. And we'll be studying these disagreements that they may have had later in class when we get to hypothesis testing, what I would consider the black eye of statistics. So we'll still study it. So you guys can decide if it's just a black eye or a bloody nose. These are the Bayesians that start evolving. And they come a little bit later. So probably this branch should be higher up too than some of these guys. So it's not exactly a true historical representation. So Dave Finetti was a probabilist. He might have something to do with the evolution of Bayesian statistics. So you can think about, what did Bruno De Finetti do? I'll point out also he was not doing applications. He argues purely on mathematical and philosophical principles. So I'll also point out on my webpage, there's a quote from Dave Finetti. For one bonus point, does anybody know what that quote says?
Probability is not real.
It's very close. Send me an email, I'll give you your point. So probability does not exist. It's an interesting thing for a probabilist to be saying. So the question is, what does it mean? Probability does not exist, yet we use it all the time. So let's come back around to that a little bit later and talk about subjective notions of probability and what Dave Finetti's trying to distinguish for us. I will interpret it very roughly as all we can ever express is conditional probabilities in the first place. We don't know the probabilities of things happening. All we can express is based off of our information at hand, how certain are we about certain occurrences happening. So we can argue about that later. So then we get some more modern statisticians that start doing applications. We've got I.J. Good, he's right here. He was in this department for about 25 years. We'll be discussing Jack's contributions throughout this class. Dennis Lindley, I would say, is obviously one of the founders of statistics. He really pushed on this. I will say that he probably did a disservice to the overall field, along with Fisher, that they're probably the two most argumentative of all of these in here. Maybe Carl gets a little bit of that too. So, but they're arguing fiercely at each other. And it's almost like dogmatics that they're arguing about. And it's very impolite. It's definitely interesting and humorous, and I kind of miss those days. I like a little bit of drama. Nowadays, you'll hear people say, well, I'm a Bayesian because I like MCMC, and it made my life a little bit easier. So when I did this Bayesian, I did this thing non-Bayesian. So I'm also a compromiser, so I think you can do both. What you want to do is understand what difference it might make in your analyses. Savage has a big contribution to Bayesian statistics, and it was lent to him through I.J. Good. Steve Feinberg outlines that very thoroughly in his paper, so be looking for their names. I'd say your modern day statisticians probably stem from these fellows. So Adrian Smith, Jim Berger, and Alan Gelfand. And Adrian Smith and Gelfand got together and they wrote the Gibbs sampling paper, which is a type of Markov chain Monte Carlo. It's a very specific type of the Metropolis-Hastings process. And so Metropolis-Hastings is a generalization of that, and we'll be studying all of those algorithms. Jim Berger was a classical statistician. He would probably say that term doesn't mean anything. He was an ardent relative frequentist. So until he started studying decision theory, and through the lens of decision theory, what are optimal decisions, he became a Bayesian. So not in his graduate work, not when he was in graduate school, but later on when he was a faculty member. So he had an interesting conversation with some Bayesians. They showed him some stuff, wanted him to work out some mathematics for it, and it changed his mind. And we'll talk about that later on when we get into decision theory. Okay, there's some comments over here. You can read through those. This presentation is on the webpage. Let's just think about Bayes' theorem. This is it, right here. What's a Bayesian? So step one, a Bayesian uses this probability statement. Now I've written it down as probabilities, that there's basically discrete sets that are compartmentalized. The C over here is the complement of everything. So it's the opposite of A. So I'm thinking about this in terms of set theory, and if we were in a math class, that's what it is. Everything's probabilities of sets. And so I like to think about things a little bit differently. So this is completely uncontroversial. This is a true rule. Let me write this down. This is Bayes' theorem. And this is the discrete case. It says probability of A given B is equal to the probability of B given A times the probability of A. Now that's the important part. There's a normalizer in here, and I'm going to write it down a little bit differently than the way I wrote it down on the board. I'm going to write it down as the probability of B. And that's what the denominator over there expresses. It's broken up into two conditional statements. I'll just point out that the probability of B is equal to the probability of B given A happens, and the probability of A plus the probability that B happens and A didn't happen. So that's the complement of A times the probability of A complement. I'm going to write this out just a little bit differently. I'm assuming A and A complement is the entire space of whatever A represents. And we can give these some meanings in a moment. But let me just write this down a little bit differently. This is the probability of B and A plus the probability of B and the opposite of A, not A. So that's what this is. So this right here is this thing. So let's just think about what this says. This says the probability of B if A happens and A happens. So when we multiply two probability statements together and they're conditionally independent of each other, we product those two things together, we get that joint probability statement. So for instance, if I said Probability of a coin landing heads or tails is a half on each. Turns out in reality it's not a half, but we can approximate. So half on each, and I talk about the probability of seeing one head. It's 0.5. Now if I want to flip the coin twice and I ask what's the probability of two heads, now I've got 1/2 and I've got a half probability of that. So the probability of two heads is a quarter. I multiply those two things together. And that's exactly the same thing that's happening here. So this is the probability of B and not A. So that's the joint probability. So then I have these two probabilities, probability of B and A happens, and the probability of B and A doesn't happen. So that's all the events that encompass whatever this event A is in the first place. So this is called marginalization. I've accounted for every possibility of A. I could break A into more sets if I would like and have more terms in my sum. But this is just what we call marginalizing out a parameter or something like that, or an event. So I've accounted for all the possibilities for A, and so I get back to the probability of just B happening. Let's just put this into some more common vocabulary. So I'm going to say the probability of, let me just write this out just a little bit differently. So what I've written out is, it's like this. I'm going to rewrite this rule right here, which is really that rule. And I'm just going to rewrite that as probability of A given that B happens. So this line means given. The random variable is A. So this is a probability statement about A given that I know B happened in the first place. So times the probability of B is equal to the probability of B given A times the probability of A. So the bar always means the right-hand side is fixed and that thing is given. That's where I will always use that notation in class. I'll break it once in this lecture and change the notation, show you a notation that other people use and why they use it in the first place. And I'll tell you what my convention is and why I use that convention. But for my class, the bar, everything to the right is fixed, and to the left, it's a random variable. Or it's at least a function of that variable. Yes,
So
please.
just to confirm that I actually get it, if you take the coin toss example and you toss two coins, the condition would come, assuming you toss the first coin, you get it heads, and then you say, given the first one's a heads, what's the probability of the second coin?
The tricky part is those are two independent events, so the probability of A given B is actually just the probability of A, because they're actually fully independent of each other.
Okay.
So this, I could adapt to that, but the conditional probabilities don't mean anything because there's no influence.
Oh, okay.
So let me give you another example. Let me say, B is equal to the, what should I call this event? I'm hungry, I'm gonna think about food. So it's always this time of the day I think about food. I'm in the mood for a chocolate milkshake, so I'm gonna write that down. I apologize to all of my vegetarians in here. I try to eat less meat all the time, but I'm in the mood for a burger. So I'm gonna think about that. This is my typical example. I've done broccoli and cheese before, but I just never feel as good about that one in the lecture. So let's just think about what this means right here. So the probability of A given B, what that represents, this set, is if I buy a chocolate milkshake, then I will buy a burger. So that's what this statement says. So if I buy the chocolate milkshake, then I'll buy the burger. And this is a probability statement about that event happening. And I'm going to buy the chocolate milkshake. So what did I just say? If I buy a chocolate milkshake, I'll buy a burger, and I'm going to buy the chocolate milkshake. So I just said I'm gonna buy the chocolate milkshake and the burger. And this is a probability statement about both things happening. So I can compartmentalize that not just as probability of A and B, the joint probability, but I can break it up into a conditional statement and multiply it by the marginal on that. And that's the same as the joint statement. So again, I can say, I'm gonna buy a burger and a chocolate milkshake, or I could say, if I buy a chocolate milkshake, I'll buy a burger, and I'm gonna buy a chocolate milkshake. I just said the same thing, I'm buying both of them. What is this over on the other side? It's the reverse statement of this. If I buy a burger, I'm gonna buy a chocolate milkshake, and I'm gonna buy the burger. So I'm buying both of them. So this is really just a statement in some way about the exchangeability of these two events, that it doesn't matter which order I do them. So I would argue that this is a relatively intuitive statement that Bayes came up with. And he was thinking about it maybe like this. I'm not sure, I wasn't there. It's hard to know how they thought because even their language is different. The way they use words, so it probably changes the way you think. So anyway, that's what Bayes' theorem is, and this is a completely uncontroversial probability statement. Everybody agrees. You can do this in cases where these aren't discrete events, but these are representing density functions. So this formula can interchange discrete events and continuous events. And in fact, this could be a density, that could be a discrete thing. So you can even co-mix these. So use density functions in it for continuous random variables, or probability statements for discrete random variables. So, and we could probably prove that, but we're going to omit that because we kind of understand what Bayes' theorem is. This is in a measure theory class. In a measure theory class, they would probably talk about a rate at which probability B approaches 0 compared to the rates up here, and talk about their differential rates. And if you ever have the pleasure of taking that class, they probably won't teach you how to analyze any data or computation, but they'll give you different ways to think about things, and they'll justify to you, this is a true statement in continuous land. That's what mathematicians like to do. So that comprised a lot of my life in graduate school. Writing proofs about things that I was like, yeah, it's kind of true, isn't it? So it just kind of depends on what you like. Unfortunately, Bayes didn't get to wow the world with this probability statement. He passed away before his paper was published. So the history of Bayesian statistics begins in 1763 with a paper written by Thomas Bayes where he outlined this rule, but he didn't actually publish it. So instead, after his death, Richard Price found the paper in his desk and thought maybe it deserves to be published. And he wrote to the Royal Society, read December 23rd, 1763, I now send you an essay which I have found among the papers of our deceased friend Mr. Bayes, and which in my opinion has great merit and well deserves to be preserved. Experimental philosophy, you will find, is nearly interested in the subject of it. I'll point out they do not use language the same way that we use language. So I think what they're saying is they're interested. So usually I might say to somebody, yeah, I'm almost interested in what you're saying. So I don't think he means it that way. And on this account, there seems to be a particular reason for thinking that a communication of it to the Royal Society cannot be improper. That your inquiries may be rewarded with many future successes, and that you may enjoy every valuable blessing is the sincere wish of, sir, your very humble servant. This is real. So it's really impressive. So anyway, the paper got published. The paper is on the Department of Statistics website, and you will not see a formula that looks like the one I just pointed out. So he says it a lot in words. Very difficult to decipher what he says in that paper. I'm going to point out next time, we make an adaptation of Bayes' theorem. Now I've changed the way I've written likelihood on this slide, and I'm only going to do this once. So sometimes people will talk about likelihoods and they'll use the notation like this. This says the likelihood of the data given the parameter set. I need to give you an example of what a parameter is and what data looks like. But oftentimes, people are really just putting in the sampling distribution right there. But they're thinking about it as a function of the parameter, and sampling distributions are functions of their data. So you're writing down the same formula, but you're thinking about it differently. Now that's a little hard to explain without an example. You will see people use this notation, and I'm going to adjust this notation, but the reason I wrote it this way for this presentation is it very much matches what we see there. So I'm thinking that our set D in this formula over here is now being exchanged with D, which is data. And we have some parameters that control the distribution. So for instance, in a normal distribution, there's two parameters. If you tell me those two parameters, I know which normal you're talking about. There's a mean and there's a variance. I'll write this down next time, but those are theta in this case. If I were trying to learn what the underlying parameters are, given all of my data. So the D might be a histogram of data from a normal distribution, and theta might be the underlying parameters that I'm going to try to learn. So what is a Bayesian going to do? I probably need to get rid of that R right there. So because it's theta is a continuum, which is not, you can't make a probability statement about points in a continuum, but rather you can make probability statements, or at least non-zero probability statements about intervals. So I'm going to adjust some of this notation because I purposefully butchered it to make it look like what we see up there. You'll notice the orders are about the same. This has the same conditional formatting that we see up there. We interchange B and A with theta and D. And down at the bottom, because theta is some continuum, I'm not adding, but rather I'm doing a continuous add, which is an integration. So, and we've all learned integration that way, where we started out with a histogram, and we refined that histogram finer and finer and finer, and summed things up, and we made it finer and finer until it limited into the same answer that you get from the integration. That's called Riemann sums, if you use kind of the flat basis function. So this is a continuous sum where I'm summing over all the values of the continuum in theta. And it looks just like this other thing. So what a lot of Bayesians will do is they'll take the function that contains your data and your parameters, they'll put it there, and then they'll operate on something called a prior distribution. And through that, we'll get the conditional flip. So what the Bayesian's trying to learn is what's the probability of your unknown parameters given that the data that you've observed. So you've seen data, now you tell me the probability and make probability statements about the things you do not know. Bayesians can do this with anything they don't know. It could be missing data, it could be change points, it could be spline knot locations, all kinds of things where it's like, where do I put these? And so you could build this up through Bayes' theorem. For the first month or so of this class, I'm going to stick strictly with parameters and distributions you might be familiar with. So we'll start with a binomial beta distribution. We'll jump over to the normal example. I don't want to start with the normal example because I find it to be a little bit confusing just because a normal likelihood and a normal sampling distribution have the same bell-shaped curve. They're just shifted in different locations. So for other examples, the likelihood might be continuous where the sampling distribution might be discrete. So I want to start with an example like that just to build up our understanding of this formula and what it actually does. But what a Bayesian is always going to do is we're going to write down the likelihood function. That's going to come straight from the sampling distribution, but the way we're going to think about it is a function over its parameters. The things we don't know, the data will be fixed. So I'm going to plug the data in there. The problem here in that is that my bar doesn't mean the same thing that I said over here, where everything to the right of the bar is supposed to always be fixed. So the way we're thinking about this is theta's actually fixed. Theta's the fluctuating thing and the data is fixed. The reason some people like flipping this notation around is that this looks like that. It looks like Bayes' theorem. So, but what I'll point out is that what all Bayesians are doing is they're taking the likelihood function and they're multiplying it by a prior distribution. So they're taking these two things, multiplying it together, and then they're normalizing it so that everything adds up to 1. Your homework 0 walks you through a discrete analog of this, where you're given likelihood values prior, so you're going to multiply those together. You're going to come up with as many numbers as there are in that grid, and then you're going to sum all those products together, and you're going to divide everything by it. And that's going to be what this thing is doing right down here. You'll notice that the denominator right here is not a function of theta. Theta is being marginalized out, so there's no theta in that equation. Usually, or I should say always, this is a definite integral. I didn't write it in right here, so you're going to be integrating over the entire space of theta. So again, we'll walk through an example. Mostly a posterior distribution that's going to tell you your beliefs about the unknown thing, given what you've actually seen, is a superposition between the likelihood function and the prior. That is all Bayes. All Bayesians agree at least on that. What they don't always agree on is which prior and why. And that's a lot of what this class is. And sometimes the computational facilities of how you even do the calculation. And so there's relative trade-offs depending on what you're doing. So we'll come back next time and we'll look at this example. Flipping a coin, and we're going to learn the probability of the actual coin. So what we will see is coin flips, and then we'll try to figure out what the probability of the coin is. What I like about this is it's a little different than what they might have taught you in Stat 101 when you were just discussing relative frequencies. So this answer will be different than what they might have taught you in an undergrad class. So we'll come back around to this, and we'll try to build up this posterior probability, the probability of the probability given the coin flips, where the coin flips are going to be encoded as 1s and 0s. So this is a fun statement to even think about. We're going to come up with the probability distribution of a probability. So that's something to think about for the first time. We'll come back next time, build up this analysis. I'll introduce you to a Bernoulli distribution and a beta distribution. And then we'll move on to normal examples. Thanks a lot, you guys. If you have any questions, I'll be around for a couple minutes. And I'll try not to do that again. Sorry about that. I'll give you your 7 minutes back at some point. Thank you. How was it?
I think I can do it prior, like the first 2 sections of the report, and we talked about the distribution earlier. I've just done more like probability analysis. So like the primary and everything. Really reminds me of turbulence data more data that I gathered and like how one set of like different factors
It's hard, yeah. Well, it has been, even though my research is on it, but